Hello, this is Warren Powell. This is part 3 of my talk on sequential decision problems from framing to model to solutions. Part 3 is on the universal modeling framework and designing policies. So this is going to be the more technical part of the talk. It's separate from the framing. Framing lays the foundation for this. So I'm going to start off with the universal modeling framework. Now, the universal modeling framework sounds complicated. The entire framework is right here on one PowerPoint slide. So in any sequential decision problem, at any time t, we have a state variable, which is whatever we know or believe. So this is our snapshot of whatever we know about our system. Then we make a decision, xt. This is something where we have a choice. And then we have the information that arrives from outside the system that I do not control. Now we've been given examples of each of these. Each time we make a decision, we evaluate performance. There can be a number of metrics evaluating performance that depend on the state and the decision. Now, decisions are made with a method called a policy. Now, this is a function that says to give me the information, the state variable, and I will make a decision. But this will be designed later. Now, this is a major point of departure with pretty much all of the other mathematical approaches for solving these problems, because they always come to this problem with an actual method. I'm going to leave this open-ended, and in the second half of this, of part 3, I'm going to actually talk about how to design these policies. Now, state variables. Tell me what you know at time t, tell me the decision, give me the exogenous information. The transition function is what then says, and here's the updated state. Now, this can be a whole set of equations, or it can just be observed in the field. Now, ultimately, I do want to come up with the best policy. That is evaluated how it works over time as the new information is coming in. Now, the universal modeling framework has 5 components that I've just gone through. These 5 components can model any sequential decision problem. So every problem on the right-hand side and any decision arrived in those settings can be modeled with this general framework. And any of the problems in any of these books can be put into this notation. And these books have about 8 fundamentally different notational systems, so this is a pretty big deal. Now, I still would like to come up with better decisions. These will be designed later. Now, so far in our framing process, we have identified the metrics. We have identified the types of decisions, but not how to make them. And we've identified the sources of uncertainty. So I'm pointing this out to emphasize we haven't covered the entire problem. I still have other parts that I have to fill in. So what comes next that we'll cover in part 3 is designing the policy. So we have to come up with how do we make decisions. Now, once we have that policy, we have 3 functions: the policy, the performance metrics, and the transition function. All of these depend on the state variable. Now, the state variable consists of what we know and what we don't know, but we have estimates. Okay, so we may have an estimate, and the understanding the state variable is very important for problems because it tells us what information we need. Now, of course, I'd like to know everything perfectly. Generally, I can't. That's why we have to use machine learning. But this whole way of viewing problems allows us to identify the information that's needed, which is very important. Now, I like to think of policies sort of like steam engines. Steam engines turn the energy in coal into a force that propels the train forward. Policies are the engines that turn information into decisions that drive companies forward. So information is like the energy going into the engine. It's just that information isn't like coal. Information is more like a buffet of all different types of food and different styles and qualities and whatnot. So this is a very good way of envisioning information. Now, I have this slide for depicting the flow of information. So anything in yellow, let's say we start off with demand and sales. So I have various things about history and sale and inputs from the sales staff. Maybe we go through some machine learning for forecasting, and the output is a sales forecast. Then I have things for production capacity with plant capacity and engines. And by the way, the same thing with the people. And these all come together, possibly with the help of machine learning, to estimate things to create my state variable. Now, this is the information that goes into the engine that makes decisions. And then out of that engine come my decisions. So this is an interesting way of depicting the flow of information, almost like it's its own supply chain. So now let's make the transition to designing policies. So I'm often asked, what is a policy? So a policy is a method that makes a decision using the information in the state variable, any method. Now, so far I've come up with almost 50 ways in the English language for words that in the right context mean how to make a decision. Okay, so this is very rich, and people making decisions is something very fundamental to being human, although animals make decisions as well. There are two fundamental strategies for designing policies. So the first one, policy search, where we're going to be creating functions where I design them to work well over time, but they do not explicitly plan into the future. Now, the second class is ones where I make decisions by planning into the future. Each of these I'm going to divide into two classes, creating 4 classes of policies. So the first of my 4 classes of policies I call policy function approximations. So these are simple rules like order up to policies. When the inventory goes below a level, order up to a level. Can be buy low, sell high policies in finance. It can be when it's cold, wear a coat. Large language models can be trained to diagnose patients and output a decision. Policy function approximations are lookup tables, linear and nonlinear models, neural networks, any function we might use in machine learning. Of the 4 classes of policies, this is the only class that does not have an embedded optimization problem within the policy. Okay, so our second category within policy search is cost function approximations. I'm going to divide this into 2 categories based on whether x is something discrete or a vector. So here, let's pretend that x is a discrete choice. It's one of a set of choices, what type of drug, what supplier, what web page design. And let's say that for each choice I have an estimate of how well it works, and I have some measure of uncertainty. Now here my measure involves a tunable parameter theta. Now, if I take this particular formula, and this isn't the only way to do this, but it's a way, what I've created is a measure of a choice x, and I want to find the one with the best measure. That's an optimization problem. Now, it's a very simple optimization problem. It's just a sort, but it's still an optimization problem, and it's subject to these tunable parameters. So this is a policy, and I can change theta to find the policy that works best. Now, if your decisions x are a vector, like let's say I'm assigning machines to various jobs, now I'm going to start using the technology of linear, integer, and nonlinear programming. Now, this is a policy, so I'm going to solve my linear program given the data, which is A, B, and C, so that's my state variable. Now, normally when people solve real-world problems, they put in tunable parameters. They sort of modify it. So I'm going to represent it this way. Now, these are bonuses and penalties and just ways to make it so that the decisions work well over time. And this has not been something that's been widely documented, but I'm now trying to formalize it. Cost function approximations are widely used in industry in an ad hoc way. So airlines optimize schedules and they put in buffer for schedule slack for weather delays. Manufacturers have buffer stocks. I stumbled across this watching grid operators planning for tomorrow, and they have the uncertainty of generators failing. So they always have to schedule extra generation capacity in case of outages. This is a very powerful method. You won't find it in any book other than mine. And chapter 13 of my big book, which I'll review at the very end of the series, is dedicated to cost function approximations. So let's now go to look-ahead approximations. So these are policies where I do plan into the future. So I like to think of Dorothy in The Wizard of Oz, where she has to decide which way to go, but she has to make a decision by planning, what's actually going to get her to her destination. Now, the first of these two classes in this category are policies where, let's imagine that I'm a manufacturing plant down in Mexico, and I need to know how much to ship to each of these distribution centers. And what I'm going to do is I'm going to come up with functions that say, if you give me this much inventory, this is how much money I will make. This is the value. Now, I don't know what I'm going to do with that. I might send it to various warehouses. I don't know what the demands will be. And so these functions are averaging over the uncertainties. So I'm indirectly planning into the future. I'm not explicitly planning. So these value function approximations are a powerful approach for certain classes of problems. But there are going to be problems where I really have to plan to the destination. Here's an example. I'm in the upper right-hand corner in Hartford, Connecticut, working with a company, Pratt & Whitney. It's 4 o'clock in the afternoon. I have to get to my home in Princeton, the lower left-hand corner. Google Maps is planning this path right through New York City using its best estimates. This is a deterministic look ahead. So I put this in a category, I call them direct look ahead policies, but I'm now, in this particular case, I'm looking ahead deterministically. Now, as a traveler, as a driver, I'm looking at this and saying, wow, going through New York City is going to be high risk. It might be bad. I'd like to maybe route around it to avoid the risk. I'm actually doing a very heuristic version of robust optimization, but there's various other techniques like decision trees and approximate dynamic programming and stochastic programming. These are entire books dedicated to how to plan into the future. Okay, so this is how rich this gets, but all of them are planning into the future where I'm thinking about decisions I might make in the future, and I might plan deterministically, but there's a number of times that I need to explicitly recognize the uncertainty. So here's a classic decision tree where I'm at this node now and I have various decisions to make. To figure out the best decision, I have to understand that uncertainties will happen, but now I still have to make decisions in the future, and then there's going to be more uncertainties and so on and so forth. So this is me planning into an uncertain future. These decision trees tend to blow up, but there are techniques for approximating these. So far I've covered all four classes of policies. The simplest tend to be the policy search policies, the PFAs and the CFAs, the cost function approximations. The look-ahead policies tend to be more sophisticated. These are the value function approximations where I use an approximate value being in a state in the future, or my direct look-aheads. Now, we use all four of these, and I'm going to claim that every human uses these, even if you don't know it, even if you're not trained in it. We have just sort of a natural tendency to recognize what is the best way to solve a problem. Now, 3 of the 4 classes of policies have embedded within the policy an optimization problem. And this can confuse people because they are solving this optimization problem, which is potentially hard, and they think, oh, once I've optimized it, I'm done. But how well the policy works depends on how well it works over time. And optimal policies are quite rare. They're only for very specialized problems. So now I'm going to make a big claim. I'm going to claim that these 4 classes of policies are universal. They cover every method for making decisions for any of the 6 types of decisions I reviewed earlier. It covers every method described in the literature or used in practice, which is why we call them meta classes. Now, this also means that any company is already using one of these 4 classes of policies. Now, you can also create hybrids. And by the way, when we humans are solving problems, we often do use hybrids, and we often switch between policies, which means you really have to know all 4 classes. What happens in the academic community is because some of these classes are quite sophisticated, we have people becoming experts in just one of the classes or even one of the subclasses, especially with the stochastic versions, direct look-aheads. Now, how to evaluate policies? It's not just who's got the lowest cost or the highest profit. There's 6 different categories. So sure, solution quality and how well it works on average over time does matter, but worst case performance, computational time, sometimes it can take a long time to solve these. Transparency, can I understand why it made a decision? Is it flexible, can adapt to new conditions? How complicated it is if I have to do the coding, and what are the data requirements? Here's a little energy storage problem. I can get energy from a wind farm. It's free, but the quantity is highly variable and I can't control it. I can get energy from the grid. Effectively, it's an infinite supply, but the price is highly random. Uh, Now I'm trying to serve a load which is fairly predictable, and I've got my Tesla Mega Pack for storing energy to help smooth over all these variations. So we created, this is the work of he was a postdoc at the time, Stefan Meisel, created 5 variations to these problems. So these were all the same energy storage problem, but the data, we played with the data. We put in different levels of noise, and the loads could be stationary over time or time dependent. And now we created examples of each of the 4 classes of policies plus a hybrid. And we made each of them work best. Now, this isn't going to always be the case, but this illustrates, and this is by the way, inventory problems are very popular. They rise all over the place. This emphasizes that you really do need to know about it, all 4 classes. Now, if you're somebody who actually writes code, yes, you're going to need to have some expertise, maybe not in all of them, but the most important. If you're in a position where you're not going to be creating the code, but you're going to be purchasing software that does these, you absolutely need to speak this vocabulary so that you can talk intelligently to the vendor. Now, how do we evaluate performance? One method is computer simulations. Some people like to call these digital twins. Now, this computer simulations, I like this. As a former academic, we were constantly building simulators. In business, people don't always have the time and the resources to build simulators. And simulators aren't perfect, although I like to think they're better than nothing. But no matter what you do of simulating, eventually you're going to have to put it in the field, and that's the ultimate simulator. Now, there's a number of settings where companies will build a tool for making a decision. They don't test it in the simulator, they put it in the field, and then stand back and watch it work. And by the way, that can be risky. There are problems where there's simply no other choice. So here's an example of a simulator for a multi-agent supply chain simulator we built for Pratt & Whitney, and we use this to test various policies. This one is a fleet simulator that I originally developed at the university. It's now run at Optimal Dynamics, and they've got the tools where they can calibrate this quickly for any new customer. And boy, do we lean on this simulator to test different parameters, because we don't want to be playing with various parameters and put it into the field where it might work poorly, because we can end up losing confidence. Now, I like to identify 6 types of policies. So take my 4 classes of policies. Now let's go to class 4. I'm going to divide the direct look-aheads into 2 classes, whether I look ahead deterministically or whether when I look ahead, I say I'm going to actually capture the uncertainty. And when I do capture uncertainty, I'm going to further divide that into 2 categories. One where the decisions are, a discrete set. I might have 5 or 10 or maybe 100. Or where the decisions can be a vector. Now, the question is, which of these are the most useful? Now, this isn't something that a theorem can answer, and by the way, numerically testing it on a small number of test problems doesn't answer this. This is a lifetime of doing testing on a wide range of problems, and here's my answer. So category 1, hands down, by far the most useful. Policy function approximations, cost function approximations, and deterministic direct look-ahead approximations. These are the go-to policies. Everybody uses it. All of us use these in our day-to-day decision making, even if I've never had any training. I can throw problems at you and say, well, how would you solve this? And I can pick problems where you would naturally run to a PFA or a CFA or a deterministic DLA. So category 2 is also useful. This is, think of decision trees. This is where I have a set of discrete actions, maybe just 2, but maybe 10, maybe larger, but not a vector. Okay, but I have uncertainty. And so there are a lot of problems where you have to make a decision, but you have to deal with the uncertainties if I'm selling a company or bidding on something. Now, category 3 is where we start to get to the arcane. This is a category based on approximating something called Bellman's equation. So this was the category used, category 3, where we had a value function approximation of the value of inventory at each plant. This is something I've worked on for many years myself. I have a 600-page book. I spent 15 years of my life, and my personal description of this is it's a very powerful strategy for a very small number of specialized problems. The academic community loves it. The books all that deal with decisions under all feature Bellman's equation, and yet it's just not something that we use very often. And then category 4 is the truly arcane, where I'm doing a stochastic look ahead, but the decision is a vector. And there's a technique called two-stage stochastic programming that is widely studied in the literature, but I don't think it's used very much in practice. Now, when you're designing policies, a good way to think of this is to imagine that you're in machine learning. And you have a problem of, let's say I want to estimate demand as a function of price, and one person comes in and says, oh, I'm just going to do a line. And by the way, this is a true story. I was working with this in e-commerce for hotels, and a very experienced revenue manager, this is what he would do. Now, you could also come in and say, no, that's just not very good. You've got to have some sort of an S-curve here, because really low price, at some point, demand maxes out, and a really high price, it'll get down to some limit. It's not going to go negative. But which function I choose is probably going to be a mixture of subjective judgment along with some formal analysis. Now, let's take a comparison of machine learning versus working with these parameterized policies. So in machine learning, I'm trying to find the best function. Here are two functions, a linear line and an S-curve. Now, finding the best function, the parameter tuning, that's usually done by an algorithm. And there's a metric, which is I want to minimize the sum of the squared errors between the training observations, the y, and whatever function I've chosen. Okay, so all of machine learning has some metric that measures how well I'm matching the training data set. Now, with parameterized policies, let's say I stay focused on category 1. Each of these have tunable parameters. I'm going to use my subjective judgment as somebody knowledgeable about the problem and knowledgeable about the techniques, and I'm going to choose among these. Then I'm going to let an algorithm do the tuning. Now, the performance metric is going to be, say a cost function or a profit or whatever performance metric that I specify. And that's a critical difference between machine learning, where it's always a distance metric, versus making decisions where I have to have a performance metric that is user specified. So I like to emphasize, always remember, it's not what tool you use, it's how you use it. And so, for example, if you like deterministic math programming, fine, but if you have uncertainty in the problem, understand that the uncertainty isn't going to go away. That doesn't mean that you can't use your deterministic math program. You just have to be more creative about how you use it. That's the end of this part. Once again, here's my webpage of links with other resources on sequential decisions.